To determine the appropriate sizes for the grounded conductor or neutral and the grounding conductor or ground in underground raceways for a three-phase 480 volts application, begin by consulting the National Electrical Code or NEC. Firstly, identify the relevant NEC tables. For a grounded conductor or neutral size, refer to NEC table 250.122 colon. For a grounding conductor or ground size, refer to NEC table 250.122 C3. Next, calculate the grounded conductor size. For feeders, NEC table 250.122 colon provides a percentage of the total phase conductor ampacity for the neutral conductor size. For branch circuits, NEC table 250.122 connect provides specific ampacity requirements. Now calculate the grounding conductor size. For feeders, NEC table 250.122 C3 provides a percentage of the total phase conductor ampacity for the grounding conductor size. For branch circuits, the grounding conductor size is typically determined by the overcurrent protection device serving the circuit. Consider these additional points. For underground raceways, ensure the raceway complies with NEC Article 300 for direct buried or underground raceways. Consider using a metallic conduit or armored cable for grounding purposes. For 480 volts applications, refer to NEC table 310.16 for allowable conductor sizes and ampacities. Ensure the grounding conductor is large enough to handle the maximum ground fault current that could flow through it. As an example, for a three-phase 480 volts feeder with a total phase conductor ampacity of 200 amps, determine the grounded conductor or neutral size. Using NEC table 250.122 colon, multiply 200 amps by 70%, which equals 140 amps. Determine the grounding conductor size. Using NEC table 250.122 C3, multiply 200 amps by 25%, which equals 50 amps. Therefore, in this example, the grounded conductor, or neutral, would be sized for 140 amps, and the grounding conductor, or ground, would be sized for 50 amps. This explanation covers the steps to correctly size the grounded and grounding conductors in a three-phase 480 volts underground raceway application, referencing relevant NEC tables and providing a calculation example. Remember that adherence to the NEC is paramount for electrical safety and proper system function. It's also important to consult with a qualified electrician or electrical engineer to ensure that your specific installation meets all applicable codes and regulations. The correct sizing of grounded and grounding conductors is critical for preventing electrical hazards and ensuring the reliable operation of electrical systems. Proper grounding provides a low impedance path for fault currents to return to the source, allowing overcurrent protection devices to quickly trip and clear the fault. This minimizes the risk of electric shock, fire, and equipment damage. In addition to safety, proper grounding also helps to reduce electrical noise and improve the overall performance of electrical equipment. Grounded conductors, also known as neutrals, carry the unbalanced current in a three-phase system. They also provide a reference point for voltage measurements and help to stabilize the voltage in the system. Grounding conductors, on the other hand, are intended to provide a path for fault currents only. They are not intended to carry current under normal operating conditions. The size of the grounded and grounding conductors must be carefully selected to ensure that they can safely carry the maximum fault current that could flow through them. The NEC provides detailed tables and calculations for determining the appropriate conductor sizes for various applications. When working with electrical systems, it is always important to follow the NEC and other applicable codes and regulations. Failure to do so can result in serious injury or death. Always consult with a qualified electrician or electrical engineer if you have any questions or concerns about electrical safety. The NEC is a comprehensive set of standards that covers all aspects of electrical installations. It is updated every 3 years to reflect the latest advances in electrical technology and safety practices. The NEC is adopted by most states and local jurisdictions in the United States, and it is also used as a model code in many other countries. The NEC is organized into chapters, articles, and sections. Each chapter covers a specific area of electrical installations, such as wiring methods, grounding, overcurrent protection, and equipment installation. Each article covers a specific topic within a chapter, such as grounding and bonding. Each section covers a specific requirement within an article, such as the size of grounding conductors. The NEC also includes a number of tables and examples to help users understand and apply the code requirements. The NEC is a complex document, and it is important to have a thorough understanding of the code before attempting to install or modify any electrical system. There are many resources available to help users learn about the NEC, including textbooks, training courses, and online forums. Always consult with a qualified electrician or electrical engineer if you have any questions or concerns about the NEC. Grounding and bonding are two of the most important concepts in electrical safety. Grounding is the process of connecting electrical equipment to the earth, providing a low impedance path for fault currents to return to the source. Bonding is the process of connecting all metal parts of an electrical system together, creating a common ground potential. Grounding and bonding work together to protect people and equipment from electrical shock and fire. When a fault occurs in an electrical system, such as a short circuit or ground fault, the fault current will flow through the grounding conductor back to the source. This causes the overcurrent protection device, such as a circuit breaker or fuse, to trip and disconnect the circuit. Without proper grounding, the fault current could flow through a person or piece of equipment, causing serious injury or damage. Bonding ensures that all metal parts of an electrical system are at the same potential. This prevents voltage differences from developing between different parts of the system, which could create a shock hazard. Bonding also helps to reduce electrical noise and improve the performance of electrical equipment. Grounding and bonding are required by the NEC in all electrical installations. The NEC provides detailed requirements for grounding and bonding, including the size and type of grounding conductors, the methods of bonding metal parts, and the location of grounding electrodes. Always follow the NEC requirements when installing or modifying any electrical system. The NEC also specifies the types of grounding electrodes that are permitted for use in different applications. Grounding electrodes are typically made of copper or steel and are buried in the earth. The most common types of grounding electrodes include ground rods, ground plates, and metal water pipes. Ground rods are typically 8 feet long and are driven into the earth vertically. Ground plates are typically 2 feet square and are buried horizontally in the earth. Metal water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. The NEC also requires that all grounding electrodes be connected together to form a grounding system. This helps to ensure that all parts of the electrical system are at the same potential. The grounding system must be properly maintained to ensure that it continues to provide a low impedance path for fault currents. Grounding electrodes should be inspected periodically to ensure that they are not corroded or damaged. Grounding conductors should be checked to ensure that they are properly connected and that they are not damaged. If any problems are found with the grounding system, they should be corrected immediately. Underground raceways provide a safe and reliable way to route electrical conductors underground. Underground raceways are typically made of rigid metal conduit, intermediate metal conduit, or PVC conduit. Rigid metal conduit and intermediate metal conduit are made of steel and are galvanized to protect them from corrosion. PVC conduit is made of polyvinyl chloride and is resistant to corrosion. Underground raceways must be installed in accordance with the NEC requirements. The NEC specifies the minimum burial depth for underground raceways, the type of backfill that must be used, and the methods of sealing the ends of the raceways. Underground raceways must also be properly grounded and bonded. The NEC requires that all metal parts underground raceways be bonded together to create a common ground potential. This helps to prevent voltage differences from developing between different parts of the raceway, which could create a shock hazard. Underground raceways must also be grounded to provide a low impedance path for fault currents to return to the source. This helps to protect people and equipment from electrical shock and fire. When installing underground raceways, it is important to follow the NEC requirements carefully. Failure to do so can result in serious injury or death. Always consult with a qualified electrician or electrical engineer if you have any questions or concerns about underground raceway installations. In the context of a three-phase 480-volt system, several key considerations come into play when sizing the grounded and grounding conductors. Firstly, the system's voltage, 480 volts, is a medium voltage level requiring careful attention to insulation and clearance requirements. Secondly, the three-phase configuration necessitates a balanced load distribution to minimize current flow in the neutral conductor. Thirdly, the type of load connected to the system, such as motors, lighting, or heating, will influence the conductor ampacity requirement. The NEC provides specific guidance on directing conductor ampacity based on the number of current-carrying conductors in a raceway or cable. This is particularly relevant for underground installations, where heat dissipation can be limited. The ambient temperature of the soil surrounding the underground raceway also affects conductor ampacity. The NEC provides correction factors for adjusting conductor ampacity based on ambient temperature. In addition to the NEC requirements, local codes and regulations may also apply to electrical installations. It is important to check with the local authority having jurisdiction to ensure that all applicable codes are followed. The proper sizing of grounded and grounding conductors is essential for ensuring the safety and reliability of electrical systems. By following the NEC requirements and considering the specific characteristics of the installation, electrical professionals can design and install systems that meet the highest safety standards. Moreover, consider the impact of harmonic currents on the neutral conductor. Nonlinear loads, such as electronic devices and variable frequency drives, can generate harmonic currents that flow in the neutral conductor. These harmonic currents can increase the neutral conductor current and may require the use of an oversized neutral conductor. The NEC provides guidance on sizing neutral conductors in systems with harmonic currents. The impedance of the grounding path is another critical factor to consider. A low impedance grounding path is essential for ensuring that fault currents can quickly return to the source, allowing overcurrent protection devices to trip and clear the fault. The NEC provides requirements for the maximum impedance of the grounding path. The grounding electrode system should be designed to provide a low impedance connection to the earth. The grounding electrode system should consist of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes. The grounding electrodes should be connected together to form a grounding system. The grounding system should be properly maintained to ensure that it continues to provide a lower impedance path for fault currents. The importance of proper documentation cannot be overstated. Maintain detailed records of all electrical installations, including conductor sizes, grounding electrode system details, and test results. This documentation is essential for future maintenance and troubleshooting. Regular inspections and testing are crucial for ensuring the continued safety and reliability of electrical systems. Conduct periodic inspections of the grounding system to identify any signs of corrosion or damage. Perform ground impedance testing to verify that the grounding system is providing a low impedance path for fault currents.